Welcome, my friends, to our discussion on heating and cooling curves. Today we're going to be talking about how to understand a heating and cooling curve at the molecular level, as well as then how can we use a heating curve and some other data to calculate the energy it takes to heat a substance through phase changes. All right, so let's get started. Before we get into the actual heating curves, we remind ourselves what temperature is. So remember that temperature is a measure of the average kinetic energy of the particles. It is independent of how much stuff you have. So, for example, if you have water that's 50 degrees Celsius and you pour half the water into another cup, you don't now have 25 degrees Celsius and 25 degrees Celsius. They're both at 50 because it's that idea of average energy of those particles. The new thing we need to talk about now is that temperature is a measure of the average kinetic energy. So any energy that goes into a system that contributes to the kinetic energy will increase the temperature. But if you absorb energy in a way that doesn't affect the kinetic energy, doesn't make you move faster, then that energy will not affect temperature. So not all the thermal energy that goes into a system is going to a system in such a way to make the molecules faster and affect kinetic energy and temperature. So that's fine. Let's talk about a couple of those. There are three of those that we're going to talk about. And let's get to it. The first type of energy that doesn't contribute to temperature is rotational energy. So if you think of this, a good analogy is a yo-yo. When you throw a yo-yo down, if you cut the string, there's like no string on it, you just throw it down, it falls really fast and hits the ground really hard, smash, right? But if you throw it the exact same way, but instead you attach a string to it, what that string does is it forces some of the kinetic energy to turn into rotational energy as a yo-yo spins around. And the faster it spins, the more rotational energy it has. But that rotational energy doesn't contribute to the kinetic energy of the yo-yo. In fact, the two of them together is equal to the energy you gave it when you flung it downward, but some is stored as rotational, and then some is stored as kinetic instead of all kinetic. What you end up with is a yo-yo that falls slower than if it wasn't rotating. This is the same for molecules. If a molecule gets hit by another molecule and speeds up, some of that energy will actually speed the molecule up. That's temperature. Some of it might actually make the molecule spin faster, and that is going to be rotational energy, and that's going to keep it from speeding up as much as it would have. So that's going to be stored as non-temperature based energy. So it won't affect the temperature, I should say. The next way we're going to look at are vibrations. So internal vibrations inside the molecule do not affect the overall speed of the molecule. So again, if you were to bash into a molecule and the bonds of the molecule were to start vibrating around, some of the energy of that bashing in is causing that vibration. So now there's less energy to speed the molecule up. So that's one way you can store. Another way you can store energy as a non-temperature based energy, non-kinetic energy. And then the final way we're going to talk about that is important today is going to be in stretching bonds. So when two molecules bash into each other, the bonds stretch between them and the surrounding molecules, and that stretching is not going to contribute to kinetic energy. It's going to be stored as chemical potential energy, as that potential of attracting and snapping back together. So that's another way energy is stored in a system that won't affect temperature, that isn't kinetic energy based. All right. So now let's get to it. So we have an understanding of now that some energy that goes into a system, and let's draw some stuff real quick. So let's say that we have a Bunsen burner or a flask here, right? And our flask's got a little water in it, and for some reason it's tipped sideways. And we've got a little Bunsen burner here. It's got a little hose there and a little flame shooting up right there, right? So we've got this thing, and this flame is delivering some heat to our liquid. And let's just say, just for argument's sake, it's 100 joules per second. And sorry, this isn't very smooth handwriting. I don't know why it's coming out as little lines like this. So that is the energy from the flame. Let's take a look at what happens to that energy as it goes into our system, into our water. Now, some of that energy is going to come in and speed the molecules up. That's going to be expressed as kinetic energy, and that is going to increase temperature. Wow, that's really bad. Most of my stuff today's lecture won't be handwritten, but right now this is doing a really poor job of making a smooth mark. So bear with me on this one. So some of the energy is going to speed the molecules up. That is kinetic energy. That's going to be reflected as increased temperature. It's going to heat the water up. But not all the 100 joules gets used that way. Because when you bash into a water, that water is not only going to speed up, but it's going to rotate some. So some of that 100 joules is going into rotational energy. So some of that joules is going into rotational energy. Some of that 100 joules actually as well is going into internal vibrations. So when they bash into each other, the bonds between the hydrogen and oxygen in the water molecule are going to actually vibrate and stretch and go all over the place, and they're going to get more chaotic, and that energy inside the water molecule doesn't contribute to its speed, so it doesn't contribute to temperature. And then the final way it's going to get, the major way, is that as they bash into each other, they're going to tend to push each other farther apart. So they're going to push farther apart. This is really getting hard to write on. I have to write a little slower. Push farther apart. And so this is stretching the bonds. All right. So again, this is an absorption of energy that doesn't affect temperature. All three of these do not affect temp. All right, this might be rough today. Bear with me. I got no other options other than this right now. Okay. So a heating and cooling curve. So basically what we do here is we start with a solid and a cold solid, say ice at negative 50 degrees Celsius. We put it into a container, right? And this device has the ability to provide the exact same amount of heat, thermal energy to our sample every single second. So it's pumping in 100 joules every second. No matter what the temperature is, this device has the possibility of doing that, right? So it's not that hard to build, but you build one. You take it from negative 50 degrees Celsius and you just heat it. And the whole time you monitor its temperature. So you take the temperature, a few times a second all the way through the entire thing. You may have done something like this in first year chemistry with a container of ice on a hot plate and just heated it up. So what happens when you do this, though, is you might say, hey, you know what should happen? If we're giving it the same amount of energy every second, its temperature should increase the same every second. It should look like this. It should be straight line, just increase, 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 right? Because we just got some more. We're just adding more energy, so it should just increase constantly. Now, what we find is that is absolutely not the case. So what we actually get is a situation where when we have a solid, this is the negative 50 degrees, we heat it, and sure enough, it heats just like we thought it would. It will heat just like this. Nice straight line. But then all of a sudden, it does something weird, and this heating stops. Although we're still adding energy, its temperature stops. And it goes straight across like that. And that happens in this weird part at 0 degrees Celsius. And what we start seeing is also the ice changes. It goes from being a solid, and then water starts forming, and starts forming, and starts forming. And over here, as soon as all the ice is gone, the moment that happens, it jumps, and the temperature starts changing again. But this time, it's less steep of a graph. And it goes up like this. And then it keeps going up. You're like, oh, okay, that makes sense again. Fantastic. But then right here at this weird thing, it goes flat over like this again. And this time, this flat lasts a long time. And as soon as this happens, we're like, oh, look, bubbles are forming. And we're like, okay, so that's boiling. And we look over, and sure enough, it's 100 degrees Celsius. This thing levels off. And then once all the water is gone, it goes up again. So it looks like this. And this time it's super steep. Like it heats really fast. So it heated like at a medium speed here. The temperature changed by a medium speed. The temperature here changed by a slower rate. Like it was slower to heat up. And then here, temperature changed much faster. Right? So of course, this is our melting point. And this was our boiling point. And at this point, we had a mix of liquid and steam. And the important thing to note here is that no matter where we sample, whether we sample the liquid or we sample the steam, both of them have 100 degrees Celsius. So the entire inside of the chamber is 100 degrees Celsius. It's not like 100 degree water and then really hot steam above it. They're both exactly the same temperature, 100 degrees. And down here we had ice and water mixture. And the exact same thing was happening here. So if you sample the water, it was 0 degrees Celsius, and you sample the ice, it was 0 degrees Celsius. A lot of people think that water turns to ice, like the transition happens just under 0 degrees, like if you're under 0, you're ice, and if you're slightly above 0, you're water. That's not true. Water can be stable and permanently stuck at 0 degrees Celsius and not be a solid at all. And ice can be permanently stuck at 0 degrees Celsius and not be a liquid and not melt. So those two things can't happen. It takes a lot of energy. You've got to go, this is a lot of energy to get across here. But they're both 0 degrees Celsius. All right. So, and then in here, of course, we have liquid, we have solid, and above this point here, we have gas. And those are the regions we'll be talking about in just a second. And we'll understand the degree of slope between these two. We'll understand should have drawn this a little longer, the length of this one and the length of this one in terms of molecular stuff. Awesome. So let's get started doing that. So region A here is the solid region right down here. So this is heating our solid from some really cold temperature up to 0 degrees Celsius for water. And during that time, the energy that's absorbed from the device, the increase in energy, is being used to stretch hydrogen bonds. And this stretching of the bonds, again, does not contribute to a temperature change. So whatever portion of energy goes into this stretching of the bonds is not heating it up. The other way that the energy is absorbed by the ice is actually speeding up the particles. So the particles move faster, but notice that not all the energy is being contributed in that way. So some of it is stretching and some is contributing to temperature and others isn't. Okay. So, and because these hydrogen bonds that hold the ice together are strong, stretching them takes a significant amount of energy. So a decent chunk of the energy that you're putting into the ice is actually going to stretch the bonds and not change the temperature of it. And that's why it has this medium slope here. It's not super easy to heat. It takes a little more effort to heat or a little more energy to change its temperature. So it's a little less steep here. All right. So region B, so our first weird region. So in region B, something suddenly happens. You go from having these ice crystals that are all set up with each other, and they're vibrating faster and faster, and suddenly that crystal structure breaks down and they can suddenly move around each other. Now that process happens quickly. Like either you're in the crystal and stuck in place, or you're moving around. You can't be kind of stuck in place and kind of moving around. If you're kind of moving around, we call that moving around. So the fact that that happens suddenly is why this thing suddenly goes flat here. All the energy in that process all the energy being put in by our heating device during this time is going to just get those bonds suddenly broken. And it takes a punch of energy to do that. So all the energy that goes in now is using to disrupt these hydrogen bonds. And I use this word here, disrupt, and that'll be key later. So as you're summarizing this, make sure you're not saying breaking. Breaking would tend to imply that we're separating them somehow. We know that when we go from solid to a liquid, that those hydrogen bonds are still holding the liquid together, right? They're just being disrupted. They're stretching a little bit farther apart. And it's happening all of a sudden, and that causes this sudden flat section here. So none of the energy that goes in during this section is going actually speeding up the molecules. All of it is going in to stretch these hydrogen bonds, and from that crystal structure to that mobile gas or liquid phase. All right, so region C here. So this is our liquid region right here. So region C, the water molecules can move freely now. So they actually have different modes of energy absorption. So they can do it in different ways. So for example, as a solid, you're stuck in place, so you can't really rotate. But now as a liquid, you can suddenly start doing things like rotating and jamming around. So even more of the energy we put in is going into non-temperature based energies, non-kinetic energy. So less of our heat is going into kinetic energy, more of it's going into these other forms like internal vibrations and rotations, and also the stretching of the hydrogen bonds in the water. And that's why this is less steep here, because more energy is going into these other forms and less is going into kinetic energy. So it's harder to heat water. It requires more energy to change the temperature of water than it does ice, and that's why. Now D. So now we get to region D, and region D is this other flat region. And at this point, as water boils, that molecule has to actually break free completely of the water. So instead of just disrupting the bonds and moving around each other, they're actually completely finally breaking the bonds and breaking away. And again, this isn't all of a sudden thing. It's not like you're kind of broken away, because if you're kind of broken away, we call you not broken away. So, yeah. So, for example, if a molecule breaks away and it's like, oh, I'm almost made it away, and it gets pulled back in, well, it got pulled back in and didn't make it away. So it's an all of a sudden thing, and that's why this thing suddenly goes flat. All the energy in this D region here is being used to completely break those hydrogen bonds and release free. So everybody at this point is 100 degrees Celsius, both the steam and the water. And the reason this takes more energy, so this is almost always on the heating cooling curve, the boiling phase is a longer stretch here, is because instead of just disrupting the bonds, you're actually having to completely break them. And we have names for these things. So this name for this amount of energy here, so the, oops. So the name for this amount of energy here is called the heat of fusion. So this amount of energy is called the enthalpy of fusion, I should say. So the delta H and a subscript fusion, and that's equal to this amount of energy. And it's some number. For water, it's like, I think it's 6.01. I have that number later on, so if that's wrong, don't hold me to it. The one I have later on is right. I think it's that, though. So it's about 6 kilojoules per mole in order to go from 0 degrees ice to 0 degrees water. Without any temperature change, you need that much energy. And then this one up here is the amount of energy it takes to go across here. The amount of energy that it takes to go across here is called the enthalpy of vaporization. Usually we just put VAP down, but it's vaporization. And that equals to this energy. And for water, it's something like 40 kilojoules per mole. Again, these numbers pop up later for more accurate numbers. But so you can see that it's significantly more because we're breaking bonds instead of just disrupting bonds. All right, last region, region E. Now, as a gas, those hydrogen bonds are already broken. So as we add more energy, we don't have to spend energy stretching the bonds. So now more of the energy can go directly into kinetic energy, and that's why we see this as the steepest one. Because like 90% of the energy is going into kinetic energy. That number is not true, but so a large portion of its energy is going to kinetic energy. Some is still being stored as faster internal vibrations in the molecules, like between the hydrogen and oxygens in the water, and some is rotational energy, but then much of it is going into kinetic energy, at least more of it, because we're not having to stretch those bonds. Okay. And that's why it can heat up. That's why steam heats up faster. Now this fusion here, or this enthalpy of vaporization, this energy it takes to go from 100-degree steam to 100-degree water, is really large in water. Completely breaking those hydrogen bonds is a rough thing to do. Remember, they're a really strong intermolecular force. So when people get burned by steam, it can be a really nasty burn, because here the steam is actually easy to cool off. You can go from really hot steam to cool steam and not really burn yourself much. The problem is that steam, because it's still hotter than your hand when it hits here, it's going to go through this entire phase change right here, dumping energy into your hand as it does so. And then when it get out, after dumping all this energy into your hand, and it's done, it's still 100-degree water sitting on your skin. So it's still going to cool off even more and give you even more energy. So it's an enormous amount of energy change, and a lot of it has to do with this, very large enthalpy of vaporization right here. All right. So now let's look at calculating energy with these things. So the question we're trying to answer is how much energy is required to heat up 75 grams of ice from negative 150 to 175 degrees Celsius. Okay. To do this, we've got to consider a few things. So first of all, remember that our heating curve looked like this. There was this medium slope, short flat, lower slope, long flat, super steep part. Each one of these sections, so A, B, C, D, and E, have a different amount of energy it takes to heat the substance. So during this region, it's medium difficulty to heat, so it takes a medium amount of energy to change the temperature. In this point, there's no temperature change, but still energy required to go across that point. In this point, it takes more energy, so we're going to have to deal with each of these sections differently as we figure out the energy it takes to go from here. And regions A, C, and E are going to use this old equation that we've used before, Q equals mc delta T. Q is the amount of heat energy required, M is the mass of the sample, C is the specific heat in that region, and delta T is the temperature change during that region. Then for region B, we're going to use the delta H of fusion, so we have to figure out how much energy it takes to go across this region. And then this up here, we're going to do the enthalpy of vaporization and figure the energy going across this region. Now, if you notice, the specific heat of a solid is a medium 2.11. The specific heat of the water is much larger because now we have rotational, vibrational, and bond stretching going on that's storing energy for us. And then as a gas, it's 1.87, so it's even lower because we've broken those bonds, and now it only has rotational and vibrational energy to store energy, and everything else goes to kinetic energy. Okay. And then here we have our values for our specific heat or our enthalpies of vaporization and fusion. So at this point, I want you to give this a shot on your own. Hit pause on the video. When you come back, I'll work through it with you. But see if you can't figure out how to take this 75-gram sample of ice from negative 150 to 75. All right, let's do this thing. So here, I want to start with region A. So this is region A, and we're going to say that we know that heating this ice up, we're going to have to go use the equation Q equals mc delta T. And we know that a mass of our sample is 75.0 grams. We know that the C of ice is 2.11 joules per gram degree Celsius. And we know our change in temperature here. Now this is the tricky part. You're going from negative 50, for region A up to 0, not the full 175, just that part right there. So our change in temperature is 50 degrees Celsius. And just to check our units, we cancel our degrees Celsius, cancel, grams cancel, and we're left with just joules. When we do this math, we get 75 times 2.11 times 50. We get 7,913 joules. 7,900, and because we have 3 sig figs here, I'm going to go with 7,910 joules. So that's region A. It takes that much energy to get from -50 to 0. Now B is a little different of a beast. We know B is 6.01 joules per mole. So if we have 1 mole, it takes 6.01 joules. If we had 2, it would take about 12, 3, about 18. So the question we have to ask ourselves is how many joules do we have? Or sorry, how many moles do we have? So to do that, we're going to take our 75 grams and we're going to convert that to moles. And we're going to say here that 18.0 grams is equal to 1 mole of water. And we got that obviously from the periodic table. We just added up those molar masses. So when we do that, we get 75 divided by 18.01. And we get 4.16 moles. So if we have 4 moles, it's going to be 4 times this, so 4.16 times that. So all this times 6.01. We end up with 25, oops, and this was actually kilojoules, sorry, kilojoules per mole. We end up with 25.0, again, 3 sig figs. This thing's getting all weird again. 25.0 kilojoules of energy. All right, so that's B. Now C is the same as up here. So C is going to be equal to, Q is equal to MC delta T. Now our mass is the same as before, so 75.0 grams. Our C is different now. It's 4.19 joules per gram degree Celsius. And then our temperature change is going from 0 up to 100. So region C gets us all the way up to 100 degrees. This is super frustrating. All right. So then I'm going to go 75 times 4.1. Actually, that should be 4.19 times 100. And I get 31,425. So I get 31,425 joules. Now it's interesting to note here that heating water from 0 degrees Celsius all the way to 100, that's a big, big temperature change, takes just a little bit more energy than melting the same amount of water. So you can see these enthalpies across here require significant amounts of energy. It's almost as much energy, so it's like, 80% of the energy it takes to go all the way from 0 to 100 is the energy it takes just to melt it, which is kind of cool. All right, so now D. This enthalpy of vaporization is 40.7 kilojoules per mole. Okay. And then we need to do number of moles, so it's just like before, so 75.0 grams. 1 mole of water is equal to 18 grams. And so I do 40.7 times 75 divided by 18. We get 170. This is equal to 170 kilojoules. Now that's really easy, or interesting, because that's 170,000 joules. And notice the energy to go from 0 to 100 is only 31,000. Just then to take that same sample and boil it, to keep it at 100 degrees but make it into steam, takes 170,000 which is 6 times the energy it takes just to heat up the water. All right, so E. Now finally we have steam. We're going to use that same equation. Q is equal to mc delta T. Oh, this is getting really fun. And then this is going to be equal to the mass of 75.0 grams times C. Now for ice, or for steam I should say, that the specific heat is 1.87. It's less because there's no bonds to break or to stretch, and that is joules per gram degree Celsius, and then times the change in temperature. So here we're going from 100 up to our top temperature of 175, so that's 75 degrees Celsius. And we do this, we're almost there. 75 times 1.87 times 75, and that ends up being 10,500 joules. 10,500 joules. All right, so that's the energy for each of our regions. Notice that these are in different units. It's in joules, kilojoules, joules, kilojoules. So I'm going to convert them all to kilojoules just to make life easier. So that's an easy thing to do. 7,000 joules is equal to 7 kilojoules. So this is 7.9 kilojoules. And this one is 3.4 kilojoules. And this one is 10.5 kilojoules. So now to find my total energy required, I have to add all these up. So I take 7.91 plus 25 plus 31.4 plus, oops, that was the wrong thing. And I get 245, about 245 kilojoules of energy total. All right, so that's the energy it takes to go from negative 50 to positive 175. Notice the fusion energies make up a huge part of that. So 205 of these kilojoules is just from phase changes breaking those bonds. So in water, that's a significant amount, and then only like 40 of the 245 kilojoules were actually needed to change the temperature in between the phase changes. Kind of a cool result. All right, that does it for today. I know the writing was a little rough. Hopefully that was helpful.